All right, so we've been exposed now to exponential functions intuitively, looking at their graphs, looking at them numerically, and looking at some of the concepts behind the exponential functions with the b equals 1 plus r. Now we're going to lay down some more formal discussion about exponential functions. First, we're going to give some definitions here. The standard format for an exponential function is the format that we're looking at here. A times b to the t power. Now, a is very much, actually it's exactly the same as a in our quadratics and polynomials. It causes the stretch or the compression vertically. Now, b has to be our base. But the important thing to take away on this first segment here is a is the initial or starting value. And so that means we've got a y-intercept point at 0a. That's going to be very helpful when we start writing equations. You might recall that when we did the problem about the stores, we had a starting value of 40, and the equation for the number of stores was equal to 40 times 1.5 to the t power. So there is the a, the starting value, and there is the b. Next, we have the, let's get this here. So we got the b number. That's our constant multiplier. The multiplier that keeps multiplying over and over again. We call that the growth factor. So b is the growth factor. And when we're trying to find b, it's often going to be 1 plus r, where r is the percent rate. Now we're also going to refer to r as the growth rate. So the growth rate and the percent rate are meaning the same thing here. Now, lastly, when we have exponential functions, sometimes they do grow, and they're going to look something like this. And that's when the b multiplier is bigger than 1. Now, if the b multiplier is bigger than 1, of course, that means r is bigger than 1. But sometimes exponential functions do not grow, they decay. And so this we would call decay. And that happens when r is smaller than 1, and so we have to have a special kind of r so that b is between 0 and 1, but it's smaller than 1. Now, all exponential functions in this basic form are going to have a horizontal asymptote at y equals 0. So I've given you a link here, and I encourage you to take that link. Pause right now even, and go to this website, take this link and add in these extra values here, and it'll pull up a website where you can manipulate the a and the b and see what happens to the way the exponential function grows or decays and how fast, depending on what a and b numbers you use. Okay, let's move on. We've got our formal definition laid out there. Let's do some examples. Okay, so first, we are given a graph and we want an equation. And we're going to work with the exponential function in the form y equals a b to the x power. And if we want this function, we need to know what is a and what is b. Well, a is the starting value. A right here is the y-intercept point. It's starting at 0, 3. So we just figured out that a equals the number 3. I'm halfway done on the equation. Now, there's a standard algebra way and an intuitive way. But we need b. And since I don't know what b is, I'm going to leave it blank. we could plug in a point, and we just so happen to have an easy point here. We have the point 1, 6. So if our equation so far is 3 times b to the x power, and we don't know b, if we could plug in an x and a y, we could solve for it. Now, we don't actually, some of you know the algebra for this, and some of you can do that no problem. And I'm going to explore that algebra in a minute here by plugging in. But before we actually do this algebra approach, I want to show you an intuitive approach. The intuitive approach is to find the multiplier. On easy problems, we can often see the multiplier. So I went up to from 3 and went up to 6. And then on the second one I went up to 12. And if we can figure out what's the pattern here. So as x goes 1, I should say delta x. So I'm stepping by 1 each time. It goes up from 3 to 6 to 12. Is there a multiplier there? Yeah, intuitively it looks like b is multiplying by 2 each time. So that's the intuitive way that you can sometimes do to get the exponential. So y would have to equal 3 times 2 to the x power. Now, after we've done the equation, we should check it by plugging it into the graphing calculator or plugging it into our table function in the calculator and make sure that we're getting these 3 points. Okay, now this intuitive approach was really easy here because the x's were counting by ones. Oh, one more detail here to help with the intuitive approach. Let's pretend that we couldn't do it intuitively and we were having trouble finding b. Now we know it's 2 already, but b is the multiplier, and if we can't figure out the b, we can work backwards by dividing. If I take this y number and divide it by the one before, that's making the multiplication work backwards. y2 over y1. Well, that's 12 divided by 6 equals 2. So if I divide these two y numbers, I get 2, which means if I multiply by 2, I'm going to get the next answer. So it turns out this division ratio is going to be quite useful for finding the b number.